In this video, we're going to cover the structure and properties of amines, as well as the uses and structure and naming of different kinds of amides. We'll also look at how amines are produced through reacting with halogen alkanes and through producing nitriles. How amines act as bases, looking at aromatic amines and the base strength of different types of amines. And recapping the nucleophilic reaction of amines which you've covered throughout A-Level Chemistry so far. Like with carbocations and alcohols, you can have different types of amines. A primary amine has one of the hydrogens on ammonia substituted with an alkyl group. A secondary amine has two of the hydrogens substituted with alkyl groups. And a tertiary amine has all three hydrogens substituted with alkyl groups. A quaternary salt has four different alkyl groups attached to the nitrogen, giving it a positive charge. An amine will have the suffix amine, and a quaternary salt will have the suffix amine ion. To name an amine, you need to identify the different alkyl, so carbon-based groups, attached to the nitrogen. In this case, we have one alkyl group attached to the nitrogen, and it contains 3 carbons, so it's a propyl group. Therefore, we would call this propyl, and the suffix is amine, so its name would be propyl amine. To name this amine, we'd need to identify the alkyl groups attached to it. And in this case, we have 2 alkyl groups. These are both ethyl groups. They both have got 2 carbons in each, so the start of the name would be di for 2-ethyl. And we then add the suffix amine. So this molecule would be diethyl amine. Again, would identify which alkyl groups are attached. In this case, we've got 3 identical alkyl groups, each with 1 carbon in. So the first part of the name would be tri for 3-methyl, so trimethyl. And adding in the suffix amine gives us the name trimethyl amine. This molecule has 4 groups attached, but would go about the process in the same way. So we would identify the 4 groups, each with 1 carbon in. Therefore, the name would start off with tetra for 4-methyl, and end in amine ion because this is our quaternary salt. So the name would be tetramethyl amine ion. If you've got multiple groups, you go about the process in exactly the same way, identifying each. So our first group has got 1 carbon in, and our second group has got 3 carbons in. So the group with 1 carbon in would be called methyl. The group with 3 carbons in would be propyl. So the name of this molecule would be methyl propyl amine. And remember, we'd make sure we put these groups on the name in alphabetical order. So M comes before P, so methyl comes before propyl in the name. The final example has got 3 different groups on, so we'll identify each of these in turn. We've got a group with 3 carbons in, a group with 2, and a group with 1. The group of 2 will be called ethyl, the group of 1 methyl, and the group of 3 propyl. Putting all these together would give us the name ethyl, methyl, propyl, amine, again in alphabetical order, E, then M, then P. We're now going to look at the uses of amines, starting off with their role as surfactants. This is a quaternary salt. We've got 4 different groups coming off the amine. We've got 3 methyl groups and 1 very long alkyl chain. We can use this kind of quaternary salt as a surfactant. The long alkyl chain at the end is insoluble, it is non-polar, so it won't dissolve in water. And the ammonium group at the end is soluble because it is polar, so it will dissolve in water. So the majority of the molecule will not dissolve in water, but the head at the end will. Surfactants are compounds which are partially soluble and partially insoluble in water. Some quaternary ammonium salts can be used as cationic surfactants, so ones which are positively charged, because they've got the long hydrocarbon alkyl group. The long chain is insoluble in water, but will bind to non-polar substances, such as grease. So if we imagine that this is a blob of grease on some clothes, the long alkyl tails can dissolve in the blob of grease, and the positively charged head groups would be able to dissolve in the water. This is because water has partial charges, the oxygen is slightly negative, and the hydrogen slightly positive. In cleaning clothes then, the non-polar ends will bind to the grease, the polar head group will dissolve in the water, therefore the spot of grease can mix with the water as a whole and be washed away, because the tail groups dissolve into the spot of grease, the head groups dissolve in the water, and the entire thing can then be removed from the clothes. Cationic surfactants are also used in things like fabric conditioners and hair products. When hair or fabric gets wet, they pick up negative charges on their surface. The positively charged part of the surfactant is attracted to these negatively charged surfaces and it forms a coating over the surface. This coating prevents the buildup of static electricity. In fabric conditioners, this is important to keep the fabric smooth, and in hair products, it helps to keep hair flat. An amide has the functional group of a carbon with a double bonded oxygen and an NH2 group attached. So we can shorten the functional group as CONH2. When naming an amide, the suffix amide is used. So for example, this amide has got 1 carbon in the chain, so its name would be methan amide. This amide has got 2 carbons in its chain, so its name would be ethan amide. This molecule is slightly more complicated to name, so we'll break down the different parts of it. We've got a chain of 3 and a methyl group on carbon 2. Carbon 2, because our amide group will always be carbon 1, therefore this is carbon 2. So the name will start with methyl, then propan for the 3 carbons in the chain, and have the suffix amide. So this molecule is methyl propan amide. Again, this molecule is a little bit more complicated, so we'll break it down. We have got 4 carbons in the main chain, and this time we've got 2 methyl groups, being on carbon 2 and 3, remembering that carbon 1 is always the carbon where the amide functional group is. So we'd start the name with 2,3-dimethyl, butan for the 4 carbons, and then amide for the suffix. So this molecule is 2,3-dimethyl butan amide. N-substituted amides are quite similar to esters. They both have a carbon with an oxygen double bonded, whereas an ester would have an oxygen, then the alkyl chain. An N-substituted amide has the amide group, and then an alkyl chain. They're named in a similar way to esters. We'll look at that in a moment. The naming format would be N with whatever the alkyl group is, amide. So for this molecule here, let's break down the different components. We've got a chain of 2 as part of our amide functional group, and then a chain of 1 as our alkyl group, which is the group attached to the nitrogen. Our name would be N-methyl to represent the methyl being attached to the nitrogen. Ethan, so we've got 2 carbons as part of the amide group. So this molecule would be N-methyl, ethan, amide. Again, to name this molecule, we'll break it down into its constituent parts. We've got a chain of 3 as part of the amide, and an alkyl chain of 2 attached to the nitrogen. So this molecule's name would be N-ethyl, because we've got 2 carbons attached to the N. Propan, because there are 3 carbons attached to the amide, ending in that suffix of amide. So this molecule is called N-ethyl propan amide. We're now going to look at the different ways in which amines can be produced. Back in the topic 3.3.3, looking at halogenoalkanes, we looked at how if a halogenoalkane is heated with excess ammonia under ethanolic conditions, this can produce an amine. So for example, if we start off with bromoethane and react this with 2 equivalents of ammonia, we'll then produce ethyl amine and our ammonium salt, in this case ammonium bromide. The problem with this method of production, though, is the amine we produce can then react immediately with another molecule of the halogenoalkane, because the ammonia will react in exactly the same way as the amine would. So we're not able to separate this out of the reaction mixture before it has chance to react again with another molecule of our halogenoalkane. This would then produce a di-substituted amine. It would produce a secondary amine. We'd have an amine with 2 ethyl groups attached. So we'd produce diethyl amine. Now the nitrogen here has got a lone pair, just like the ammonia did, just like the primary amine did, so this reaction could then happen again. Our diethyl amine could then react with some more of the halogenoalkane in the reaction mixture. So we would have our halogenoalkane, our bromoethane, reacting with diethyl amine to produce, in this case, triethyl amine. We'd add another ethyl group on. And this reaction could then happen a third time to ultimately produce a quaternary ammonium salt. So the problem with this method is that the reaction will keep on happening until we end up at this endpoint here. We'll end up with a mixture of products. We'll end up with a mixture of our ethylamine, diethylamine, triethylamine, and our tetralethyl amine ion. That mixture of products is not desirable because we want to try and make one amine only. So we're going to now look at a second method of producing amines, which will only produce one amine. So this is a better method to use for the production of amines. and this involves two stages. The first of those is the nucleophilic substitution of halogenoalkanes using cyanide ions. So for example, we could react bromomethane with potassium cyanide, and this would produce ether nitrile with potassium bromide. This is a reaction you looked at in the halogenoalkanes topic 3.3.3, so if you're unsure on this reaction, revisit that for the nucleophilic substitution mechanism. The second stage in this reaction, which is something you've not looked at before, involves reducing our nitrile. We will use lithium aluminium hydride in the first step to do this, followed by dilute acid. Similarly, when you looked at the reduction earlier on, when you're looking at aldehydes and ketones being reduced to alcohols, we used H for hydrogen in a square bracket to represent the reducing agent. We do the same here to make the equation simpler to write. So you need to know whatever nitrile you use is reacted with 4 equivalents of the reducing agent, with lithium aluminium hydride in step 1, dilute acid in step 2, and this produces an amine. You need to be careful to make sure you label these as step 1 and step 2. You also need to be careful that we are adding a carbon from our starting material to our end product. To make ethyl amine, we started off with bromomethane, because during the conversion to a nitrile, we add on a carbon. So if you're given a target molecule to make, your starting material has to be 1 carbon shorter because you're adding a carbon on as part of the process. Lithium aluminium hydride is a chemical we could use in the lab on a small scale. However, it's too expensive for wide-scale industrial use. In this case, we'd use catalytic hydrogenation instead. We'd react our nitrile with 2 equivalents of hydrogen using a metal catalyst, typically nickel or sometimes platinum, at a high temperature and pressure, and this would give us our same end product. You need to know both of these methods. You need to know the reduction with aluminium hydride is used in labs on a small scale. You need to use that catalytic hydrogenation is used for industrial use, as lithium aluminium hydride is too expensive. So you have to be able to write equations just like this to show how you can go from the nitrile to the amine. We're now going to look at aromatic amines. So aromatic amines are amines with a benzene ring attached. You need to know what the use of aromatic amines are, and they're used in the manufacture of dyes for things like clothes. Be really careful to make sure you say they're used in the manufacture of these products. They are not dyes themselves, they're just used as the wider process to produce dyes. To produce aromatic amines, we reduce nitrobenzene. So as a quick reminder from the aromatic chemistry topic, this is what nitrobenzene looks like. And just like we looked at with the reduction a moment ago, we'll use H as our reducing agent to make the equation simpler to write. In this case, we need to use 6 equivalents. Because if you notice, we've got 6 additional H's on this side of the equation, 2 in the NH2, and 4 in total from the 2 molecules of H2O. So the reagents we use for this process is tin with concentrated hydrochloric acid under reflux conditions, and then in a separate stage, we use sodium hydroxide. That then reduces the nitro group to an amine group. As before, you need to make sure these steps are clearly labelled 1 and 2, otherwise you won't get the marks in the exam. If we added both of these reagents together, which would be implied if you didn't number them 1 and 2, the acid would neutralise with the base and you wouldn't get the desired reaction. So you need to make sure for this equation that you include 6 equivalents of your reducing agent, use tin and concentrated hydrochloric acid in reflux conditions, then in a separate step use sodium hydroxide. This will produce your aromatic amine with 2 molecules of water as a byproduct. We're now going to compare the base strength of different amines. All amines are weak bases. So this means that they will all accept protons, H+ ions. They do this through the lone pair on the nitrogen forming a coordinate or a dative covalent bond with the hydrogen ion. So for example, we've got our amine here and a hydrogen ion. The nitrogen has a lone pair, and it can form a bond with the H+ ion, forming an ammonium salt. Base strength is defined as how available the lone pair on the nitrogen is. If there is a higher electron density on a particular atom, so in this case the nitrogen, we say that the lone pair is more available, therefore it will be a stronger base. As if there is a higher electron density, it is more likely to be able to accept that proton, therefore making it a stronger base. So you need to be quite confident in how you can describe what base strength is. So a higher electron density, meaning a more available lone pair, therefore more likely to accept a proton, therefore a stronger base. And to be able to give the precise definition that base strength is how available a lone pair is. And you've got to use this term available in your answer when you're comparing different bases. We're now going to look at each kind of amine in turn and look at how available or not available its lone pair is. We'll start off by looking at primary aromatic amines. So an amine which has only got one group on, aromatic, in this case that group is going to be a benzene ring. So this is what a primary aromatic amine would look like. And our lone pair is on the nitrogen. Primary aromatic amines are weak bases. If we recall what a benzene ring is, it is a delocalized system of electrons. So right next to our nitrogen with the lone pair, there is a delocalized ring here. This delocalized ring pulls the electron density from the nitrogen, from its lone pair, towards the delocalized system. It will make it more stable. So therefore, the nitrogen lone pair is partially delocalized into the benzene ring. This means that it will decrease the electron density on the nitrogen, therefore making the lone pair less available, therefore making primary aromatic amines weak bases. The electron density from the nitrogen is being pulled into the ring, therefore that lone pair is less available to attack and react with a hydrogen ion. We'll now look at primary aliphatic amines. So aliphatic means it's alkyl chains, so it'll be an amine with one straight chain attached. So we can see here, primary amine, we've got one R group, and we've got our lone pair on the nitrogen. Whilst all amines are weak bases, primary aliphatic amines are stronger bases than the aromatic amine we've just looked at. And that's because if we look at our lone pair here, there are no groups to withdraw the electron density away from the nitrogen. In fact, we've got an alkyl group here, which will actually push electron density towards the nitrogen. If electron density is being pushed towards the nitrogen, that's going to make this more available because it's got a higher electron density and therefore be a stronger base. So we can say that the alkyl group pushes electron density onto the nitrogen. Therefore, the lone pair is more available, which is why primary aliphatic amines are stronger bases than primary aromatic amines. Finally, we'll look at ammonia. So ammonia is NH3, and the lone pair is on the nitrogen. The base strength of ammonia is somewhere between that of an aromatic amine and that of an aliphatic amine. And that's because there are no groups to withdraw the electron density away from the nitrogen, and there are no groups to donate the electron density towards the nitrogen. There are just 3 hydrogens which don't really do anything, so it's straight in the middle between the aromatic, which has got the electron withdrawing benzene ring, and the aliphatic, which has got the electron donating alkyl group. We'll now summarise the different base strength of amines. So our weakest base will have the lone pair being least available, and our strongest base will have the lone pair being most available. So our aromatic amine is the weakest base, ammonia is in the middle, and our aliphatic amine is the strongest base. So our lone pair on the nitrogen in the aromatic amine is affected by the delocalized electrons on the benzene group. So that lone pair, the electron density on the nitrogen, is pulled into the delocalized ring, lowering the availability of that lone pair. For the ammonia, the lone pair on the nitrogen doesn't have anything to push electrons towards it or take them away from it, so it's slap bang in the middle. For our lone pair on our aliphatic amine, it has the donating group of the alkyl group, meaning that that lone pair is a lot more available because it's got the electron density being pushed towards the nitrogen. We're now going to summarise the reactions of amines which you've studied across the A-Level Chemistry course so far. The first reaction is that of nucleophilic substitution, covered in the halogenoalkanes topic. And this is where 2 equivalents of ammonia react with a halogenoalkane to produce an amine and an ammonium salt. Remember that the product of this reaction can react again with the halogenoalkane in your reaction mixture, producing amines with multiple alkyl groups substituted on. So be prepared to write multiple iterations of this reaction. So the mechanism involves the halogenoalkane and the amine. In this case, I'm going to show you the example of how we would produce the dimethyl substituted amine. We'd draw on our lone pair of electrons. And for the nucleophilic substitution reaction, the lone pair attacks the carbon and we break the carbon-chlorine bond. This would be the same for any halogen in this position. Our intermediate product has our nitrogen having a positive charge, as it's now gained an extra bond. So we need a final curly arrow showing the loss of the hydrogen. And this is how we'd ultimately form our ammonium salt, but we don't show how this is formed in the mechanism. The second example of the reactions of amines we've looked at is where acyl chlorides react with primary amines to form N-substituted amides. So for example, we've got our acyl chloride here. This is ethanol chloride, and we're going to react it with methylamine. This will produce our N-substituted amide, in this case N-methyl ethan amide. Remember, any reaction with an acyl chloride will produce hydrochloric acid. You need to make sure you can name all chemicals involved, So we've got ethanol chloride reacting with methylamine to produce N-methyl, so the one carbon here, ethan amide because there are two carbons in the main chain. To draw the mechanism for this, we draw out our ethanol chloride and our methylamine. We'd add the lone pair onto the N. Our first arrow in this nucleophilic addition elimination mechanism is from the lone pair to the carbon. Our second arrow is from the carbon-oxygen double bond up to the oxygen. And this forms our intermediate product, with the nitrogen having a positive charge and the oxygen a negative. We then draw our lone pair on the oxygen and show that moving to reform the double bond, whilst removing the chlorine. And finally, we lose the hydrogen to remove the positive charge on the nitrogen. The final reaction of amines we're going to look at is where acid anhydrides react with primary amines to form N-substituted amides. This process is exactly the same as with the acyl chlorides we've just looked at, but you don't need to draw a mechanism for it. So we'd have our acid anhydride reacting with an amine, producing our N-substituted amide, but this time we'd form a carboxylic acid rather than hydrochloric acid because we're using an acid anhydride rather than an acyl chloride. As before, you've got to name all chemicals involved, so you should be able to say this is ethanoic anhydride reacting with methylamine to produce N-methyl ethan amide and ethanoic acid.